Hello everyone. I'm Chen from the Hong Kong University of Science and Technology, and today I'm very happy to share our ongoing work, ClearAgent, Agentic binary analysis for effective vulnerability detection. This is the presentation will have 4 parts, and let's begin with the background. The binary code is the final artifact of the software building process. So from left to right, the source code will be compiled first to the IR, also known as the intermediate representation, and then to the assembly code, and finally to the binary code, which is essentially a bunch of bytes. And during the process, the high-level information such as types and symbols will be stripped. So in the opposite directions, the reverse engineering techniques will first performs some subtasks such as the type inference and variable recovery to try to translate the binary code back into the code formats that are corresponding to the each stages in the compilation process. For example, we will first have the disassembly code from the binary, and then the lifted IR code from the assembly, and then the decompiled pseudocode from the IR. And program analysis technique can be applied to each of these formats in the reverse engineering process. And the binary code analysis is crucial for detecting vulnerabilities in common off-the-shelf software when the source code or the building process is not available. And there remains lots of challenges in the binary analysis. Some of them are the traditional challenges that the understandability of static analysis and the requirement of a huge amount of human expertise, for example, the modeling of functions. And there also exists some new challenges, appears new challenges in the area of LLM, which I would call the fragmentation, which is that although some LLMs have been trained for specialized subtasks such as the variable recovery, it is still hard to merge the knowledge for comprehensive binary understanding, and each LLM may require their own prompt engineering scheme. So there are also some hallucination problems. So we will set our direction to let LLM to interact directly with those mature binary analysis tools in a guided manner. And this paradigm actually aligns with the currently very popular LM agent. So the agent, by its traditional definition, is something that can perceiving its environment and acting upon that environment. And for an LLM agent, it works like in the pseudocode. So in the main loop, there are performing two main steps, and each steps and the agent can optimize for each step towards the agentic workflow. So in the binary analysis scenario, we instantiate the agentic principle to first help LLM agent to understand binary code, and second, to guide LLM to explore the binary. And let's discuss our motivation. So we have do a preliminary study on the current binary analysis agent, and we have find that they actually do not follow well on the previous two principles. The first one is that they have a cooperation gap between the different binary code formats. So they only provide either a decompiled code or the disassembly code, and each of them have their pros and cons. The decompiled code is concise, but might have some fidelity issues, such as the wrong stack length. And for the disassembly code, it is faithful to the binary, but it's low level and verbose for LM to understand. Yeah, that's the first limitation. And the second one is that the previous binary analysis agent only explore at the function level, which means that they just provide the whole function body to the LLM and let them to reason. But due to the recent study, it shows that the LLM cannot correctly reason the control flow and data flow, even given the source code, let alone the binary code. So here is a simple example that I fetched from their trajectories. So given the decompiled pseudocode, LLMs just cannot reason it correctly and just decompile it again, and that is actually might have a cascading effect, which led them to hallucinate on this next action and finally exit the context length. So given these challenges, we propose our ClearAgent framework. So it's designed as a generic framework, but in the following, I will use the bug detection as the downstream application. So our agent mainly features two tool sets. The first one is the binary language server, and the second is the context manager. They are all defined in this interface. So the whole agentic workflow is in the clockwise direction. Given the system prompt and the exploration strategy, the agent will first translate the binary file into the three analyzable code format, which is the disassembly, IR, and the pseudocode, using the purely symbolic binary analysis tools such as the Ghidra and our in-house binary lifter, Plankton. And then the agent will iteratively query the binary code through the binary interface. And finally, if it finds a bug, it will validate it and then outputs a bug report with the proof of concept scripts with its best efforts. And now let's briefly discuss the details about the two core components in our binary interface. The binary language server aims at providing a friendly interface for LLM to understand binary code. And the friendliness comes as twofold. The first is called the LLM friendly, which means that we have provided a mapping between these three formats of binary code and help the LLM to understand the binary code in a unified way. And the second is analyzer friendly, which means that we use the IR as the primary query target for LLM because IR itself supports the symbolic analysis and yes. So let's skip these details and just watch this example. So here is the three binary code formats for a CVE, and so our agent will first look at the decompiled code and understand its main logic, and it seems that it have a command injection bug, and then it will query the corresponding IR to the getEnv function call, and here it then performs the symbolic analysis on the IR from the time 40 and to 41, and then all the way to the printf here. And after this process, the LM might have assumed that this is a command injection bug, and then it will query the assembly code for if there is any fidelity issues. Okay, the other component is the context manager, which is to guide LLM agent to explore the binary at both the function level or the basic block level. And the contexts are updated with each query to the binary language server. So at the function level, it will record the visit on the sub call graph, and at the basic block level, it will record the visit on the sub control flow graph. So and the context is used collaboratively with the strategy. For example, for typical bug detection, we need to analysis and then validate it. And for each phase, the strategy we borrow the strategy from previous reverse engineering study here. It can perform either backward, forward, or BFS, DFS. Here is a simple example. So this is a whole view of the binary, and the darker the color, the more visit. And so the agent might first visit the man, and then here, and inside this function, it has a record of the visits. So let's briefly discuss the preliminary evaluation here. So for the first component, the binary language server, we want to know if the LLMs can really understand the binary code. So we choose the 19 binaries captured flag challenges that can be solved by the current state-of-the-art CTF agents. And they're either Pong challenges or reverse engineering challenges. So our metrics is that if it can identify the buggy point in the Pong challenges, and if it can understand the flag in the reverse engineering challenges, and our agent can achieve a comparable performance, and it is noted that it's only on the early version of ClearAgent. So there are also some unsolved challenges here, and we classify them into two limitations. The first one is the inaccurate IR. So the disassembly may have some obfuscation, so the LM cannot reason it. And the second one is the lifter bugs. So the lifter have produced a wrong IR, but this now can be fixed by querying by the synchronized query. The second limitation is the insufficient guidance. So yeah, although many capture flag challenges binaries are small, but there are also some C++ binary with a deep calling context in the library functions, and so it's hard to guide them. And the second one is the indirect call targets. So this indirect call is dynamically computed. So it's hard. It cannot be analyzed by our tool. And the second evaluation is about the context manager. So we reproduced a historical CVE in the IoT firmware, and including these three phases. The first is to recover the handler dispatcher logic, and then analyze the command injection bug in the handler using the binary language server. And then in the validation pass, it will perform a backward analysis and find the setenv source that comes from the web packet, and it will finally produce a payload like this, which will help the reproduction of the CVE. And we envision the following three future directions of our agent. The first is the agentic IR refinement, which we can think of like the renaming and retyping functionalities in IDA Pro. So the lifting or the binary analysis is not a one-time effort, and we should give it the functionality to iteratively refine the IR or the decompiled code. And the second one is the multi-binary analysis, which is a typical kind of scenario in the IoT vulnerability, and it requires you to understand the interprocess communication between binaries. The third one is the huge binary analysis, which might let LLM to perform some uninterested function. And that's all. I'm happy to take questions.
Hi. I want to ask that is the performance of the LLM depend on the precision of your static analyzer?
Yes. It's a great question. So that's why we need to design the validation phase. It's like it will. So in the binary language server, we will collect the path here and the path condition here. So in the validation phase, we can we will examine the path conditions and to facilitate the path sensitive analysis.
Okay, I mean the precision. For example, the pointer analysis can analyze the indirect calls in binaries.
Yes.
And I mean that if the precision of that indirect call analysis will influence your performance of the.
Yes, it will. So currently, the point analysis is done by our symbolic tools. It's not done by LLM. So it's different from the previous two works.
Okay, thank you.
Okay, I have a question. Based on experience, writing a workflow with predefined prompt or function calling is often more effective and less costly than agent. At least that's my experience in binary lifter.
Yes.
What do you think of this problem?
Yes, if you focus your scope on the tent analysis, I think you write a predefined prompt is great. Is the latte, that latte work, right?
Yeah, yeah.
But not all vulnerabilities are 10 styles, and we and the source and things you still need to model them, and I think LLM can leverage its wide knowledge base to identify the wider scope of the vulnerabilities. Yes.
Okay, thank you.
Yeah, thank you for the questions.